Hi, and welcome to the Implementing and Administering Cisco Solutions CCNA 200-301 video series by EC Council. My name is Glenn Singh. In this video, we'll take a look at explaining the roles and functions of various network components. So let's dive on in. One of the very first and foremost questions that we all need to be able to answer, especially if we are going in the field of network engineering, is what is a network? To put simply, a network is two or more computers, but in today's world, we have smart devices. So we can say, just generally speaking, it is two or more devices that are interconnected together for the purpose of sharing a resource. A resource can be anything. You can connect to a network to share files via a centralized file server. You can connect to a network to send documents to a network printer to, of course, print documents. Furthermore, we use the internet, which is the world's largest network, to exchange emails and even WhatsApp messages. If you are a gamer, you connect to the internet to play multiplayer games with your friends. And all of these are simply examples of network resources. Furthermore, network resources are not limited to the items that I've listed here. We create networks to even create or support voice over IP systems. In today's world, voice over IP and video over IP, such as teleconferencing, is such an important thing. Many persons are using a lot of online collaboration applications such as Zoom, Cisco WebEx, and even Google Meet to even deliver content to other users around the world. Another important question is what makes up a network? What are the actual components? What can we find on a network? So let's take a look at what are these network components and the items that we can find. On a network, you'll find various types of components. You'll find routers, layer 3 and layer 2 switches. You will also find next generation firewalls and even intrusion prevention systems. The firewalls and the IPS are security appliances. You'll also find access points and even wireless routers. There will also be controllers, which is Cisco DNA Center, and even wireless LAN controllers. And we cannot forget about endpoints and servers. In the early days, hubs were created to interconnect end devices together, such as computers to intercommunicate. However, in today's world, hubs are now obsolete in the networking industry. To put simply, hubs simply take an incoming signal and repeat it out of all other ports. For a small network, this may not be a problem, but for a larger network or as a network grows, this may create many problems, such as broadcasting unnecessary traffic around the entire network. Devices that are not intended to receive messages, the hub will still send messages to them. In this diagram, we can see there are 4 devices that are connected to a hub. There's PC1 to 4. We can see here PC1 is sending a message to PC3. However, when the hub accepts a signal, the hub regenerates a signal out of all ports except the port the signal originated on. The message will be sent to PC3 as intended, but a copy of the message is also sent to PC2 and PC4. Now this may be a security problem, simply because the message was not intended for PC2 and PC4. So to get a better idea, let's take a look at a lab on Packet Tracer. To follow along with this exercise, you can download the pre-built Packet Tracer lab. My labs are located on GitHub. You can go to the URL as indicated here, which is github.com/glenndsing/codered-ccna-200-301. At the time of this recording, there isn't much labs available, but as time progresses, I will add extra domains together with the lab files in this region. To find the labs for Domain 1, simply click on Domain 1, Network Fundamentals. And you can download Lab 1, which is demonstrating the functions of a hub. Once a file has been downloaded, simply open it with Cisco Packet Tracer. As you can see, we have 4 devices connected: PC1, PC2, PC3, PC4. Each of these devices are already allocated an IP address. To get a better idea, to see how the hub functions, on Packet Tracer, we can click the simulation window. Once we click on simulation, we can click on Edit Filters and ensure that only ICMP is checked. This will show us all the ICMP messages that are being sent between the network. Next, let us click on PC1. Then we can click on the Desktop tab. Next, click on Command Prompt. And let us perform a ping between PC1 and PC3 and observe what happens. As you can see, the message is created on PC1. So let us click Fast Forward to forward the message. The message now reached the hub, and the hub sends it to all other devices. You can see with the X icon indicator PC2 and PC4, they are going to discard the message because the message is not intended for them. However, PC3 will accept and respond. PC3 responded and sent the message back to the hub. But let's take a look at what happens next. The hub broadcasts it to all other devices. You can see PC1 will process it, while PC2 and PC4 will discard the message. And this here is a clear example of how the hub actually works and functions in terms of broadcasting messages. Simply imagine that there's a network of probably 50 more devices and there are many hubs. When one device sends a message, all the hubs will accept and rebroadcast that message out of all other devices. However, there's another challenge when using a hub network. Only one device can transmit at a time. If 2 devices are transmitting simultaneously or at the same time, a network collision will occur. To prevent such a collision, there's a technology called Carrier Sense Multiple Access Collision Detection. Carrier Sense simply indicates that a device, such as a PC, will check the media to determine if anyone is transmitting. So it will literally sense the wire. Multiple access means that multiple devices are currently trying to use the media, which is a network cable, at the same time. Collision detection is the actual mechanism that is going to be used by end devices to ensure that they will send a message only when no one is transmitting, so therefore a collision will not occur. Put simply, CCNA CD defines how a network will respond when 2 devices are attempting to communicate simultaneously on a wired Ethernet network. Before a device sends a message on the network itself, the end device will check for any sort of signal that is being transmitted on the wire. If a signal is found, the device will wait and check again until no signal is found and then transmit its message. When a device is transmitting a message on a network, the signal will be present on the same segment. This method prevents collisions on a wired network. However, on a network with switches, this technique is not needed. So let's imagine we have 4 devices again. We have A, B, C, and D. If A sends a message and B sends a message, a collision will occur on the hub, and therefore both devices will have to retransmit until the message is successfully delivered. With CCNA CD, if A wants to send a message, A will check the media or the medium, which is a wire here. to determine if there's anyone transmitting a message. A will wait until a predefined time passes and recheck again. If there's no signal, A will transmit a message. And this happens only on a hub network. As you can imagine, this is a difficult thing. We no longer use hubs anymore in today's network. What we use are smarter devices. These are network switches. On a network, you will commonly find switches. Switches are considered to be intermediary devices that are used to interconnect end devices and other network components. Without switches, your computer will not be able to connect to the actual network itself. Keep in mind, switches are used to extend a local area network. If there are many devices on your network and you need to interconnect them, switches can make this happen for you. In the field of networking, there are two types of switches. There are layer 2 switches and there are layer 3 switches. Layer 2 switches are able to extend a network and forward frames to their destination by simply observing the destination MAC addresses found within a frame. Each frame to enter an interface on the switch, the source MAC address is recorded and stored in a special area. This is known as a Content Addressable Memory Table, or the CAM table, on the switch. Therefore, creating a table which has each port on the switch and the location of each MAC address. Therefore, in future, whenever a frame enters a switch, the switch can simply perform a lookup in the Content Addressable Memory Table and determine where the destination MAC address is located on, and simply forward a frame out of that port. Here we can see another diagram, but instead we have a switch connected on the network. In this example, PC1 wants to send a message to PC3. When PC1 sends a message to the switch will look at the destination MAC address and simply forward the frame directly to PC3. So as you can see here, a direct connection is built between PC1 and PC3. The switch does not forward the frame to PC2 or PC4. So let's take a look at a Cisco Packet Tracer lab, which is called Lab 2 on GitHub, demonstrating the functions of a switch. To follow along, download and open Lab 2 on Packet Tracer. Now that the lab has been opened, let us perform a ping test between PC1 and PC3. Firstly, let us click on Simulation so we can have a better idea of what a switch does. Ensure the filters are set to ICMP as recommended before. Click on Edit Filters and ensure ICMP is checked. Next, ping between PC1 and PC3 on this network. So click on Desktop, then click on Command Prompt. Let's type ping, followed by the IP address of PC3. As we can see, the message is created on PC1. Next, the message is sent to the switch. The switch forwards a message directly to PC3 only. PC3 responds, the message is sent from PC3 back to the switch, and the switch forwards a message back to PC1. So, as you have noticed, the switch does not send a message or rebroadcast a message out of all ports. The switch will only send a message to the actual destination. Be sure to try out this lab before moving on. Another type of switch is layer 3 switches. Layer 3 switches operate at both layer 2 and layer 3 of the OSI model. This means they have the capabilities of reading both MAC addresses of a frame and the IP addresses of packets. Layer 3 switches are used to provide basic routing capabilities without having the need to implement an actual or a dedicated router on the network. So far, we've talked about layer 2 and layer 3 switches, but let's take a look at how these devices look. So let's head over to Cisco website. Now that we're on Cisco website, let's click on Products. Let's head over to networking and now switches. Let's click on products one more time. And here you can see we have different switches. Each of these switches are designed to be implemented in a certain part of the network. We have access layer switches, we have compact switches, we have even core and distribution switches. There's also data center switches, small business switches as well. Simply by clicking on any of these models here, you'll get a better idea of their capabilities, functionality, and even their port density. The port density simply indicates a number of ports that are available on a switch. It also will be able to tell you whether a switch is modular or non-modular. Being a modular switch, additional ports and modules can be installed on the switch. A non-modular switch simply means it is as is on the description. There is no additional modifications can be made. Thus far, we mentioned that switches are able to extend our network. However, what if you want to connect more than one different network together? Whether it's different in media, whether it's different in IP, we will need a router. Router is a device used to interconnect two or more different networks together. These devices simply observe the destination IP address found within the header of an IP packet. Then it uses the routes found within the routing table to make its decision to forward the packet to their intended destination. Since routers are able to read and understand IP, which is IP protocols, they are considered to be layer 3 devices, while switches mostly operate at layer 2. Routers, however, are layer 3 devices, simply due to their capabilities of reading IP information found within the packets. Let's take a look at this diagram. On one side of the router, there's a private network, which is most likely your home network or your organization network. On the other side, there's the public network, which is the internet. The protocols that are used on the internet is different from those that are used in your private network. The type of technologies would vary as well. To be able to connect your personal or your private network to the internet, a router is required. If you're a home user, you will have a modem. Within your modem has router features or it has routing capabilities. So, to put simply, your modem is also a router at home. To get a better understanding of how the router works, let's take a look at doing another Cisco lab. On GitHub, you can download Lab 3, which is demonstrating the functions of a router, and open it with Cisco Packet Tracer. As you can see here, we have a couple of devices. We have one PC, two switches, one web server, and one router. Keep in mind that we actually have two networks here. The first network, let's call this network A, and the second network, let's call this network B. Each interface on a router must be connected to a different network, whether it's a different IP subnet or a different IP network generally. So, simply by watching this diagram, there are two interfaces on the router that is currently being used. One interface has the IP address of 192.168.1.1, while the other interface has 172.16.1.1. So the objective is we are going to take a look at traffic that is moving from PC1 and heading over to the router, then the router will forward it to the web server. So let's actually see what happens on this network. Be sure to click Simulation. As always, ensure the ICMP filter is turned on because we are going to send a ping packet from PC1 across to the server. So let's click on PC1. I'll drag this down here and click on Desktop, Command Prompt, and ping, and the IP address of the web server. And hit Enter. So now we can see a packet is created. If we double click on the packet, we'll see the contents of this message. We can see the destination information. We can see layer 3 IP header. We can see the source IP address, which is that of PC1, which is 192.168.1.10. We can see the destination IP address, which is 172.16.1.10, which belongs to the web server. So let's forward this message and see what happens next. Let's click on it one more time and take a look at this very interesting information here. Now, the message contains layer 2 details. This here is a source MAC address of the PC, which ends with CC2E, whose MAC address is a destination's MAC address that ends with 5901. This MAC address belongs to the router. And you may be wondering, wouldn't the destination MAC address belong to the web server? Well, to put simply, all local area network communication, they uses MAC addresses to communicate, not IP addresses. And since that the switch is a layer 2 device, it will not be able to see who the destination IP address is. The switch strictly relies on the destination MAC address to make its forwarding decision. As long as the PC is sending data to its default gateway, which is the router, it will use the router's destination MAC address. So let's forward this message and see what occurs next. So now the PC has sent the packet to the switch. The switch now sends it to the router. The router will send it over to the server. So let's take a look at the packet at this point. Notice that the source and destination MAC address has changed. The source MAC address belongs to Gigabit Ethernet 0/1 of the router. The destination MAC address has now changed to being the MAC address of the web server. So please keep in mind that the MAC addresses always change as it passes between different layer 3 devices altogether. So let's leave this to play out as it is. We can see the server received a message and is replying. It sends it back to switch 2, then to the router. The router will then send it to switch 1 and back to PC1. Furthermore, let's head over to Cisco website to have an idea of what routers do look like. And again, similar to switches, we have routers of different shapes and sizes. There are routers for branches, there's routers for WAN aggregation, there's edge routers, there's even service provider routers. Another important device that you'll find on a network is actually a security appliance known as a next generation firewall. Firewalls are typically used to filter malicious or unwanted inbound and outbound traffic off a network. However, with the rise of botnets, ransomware, and even advanced persistent threats, legacy firewalls are no longer capable or even efficient to prevent these modern-day threats. Next-generation firewalls are simply designed to monitor, detect, and even prevent any existing and new and emerging threat that may arise. Typically, you will install your next-generation firewall at your network perimeter. Therefore, the firewall should be the device that is facing the internet, simply because the internet is considered to be an unsafe or an untrusted network, because there are many bad threat actors, and there's also a lot of viruses and malware. So let's head over to Cisco website to see what are firewalls. As you can see, there are different sizes and models of firewalls. The size and model of firewall simply depends on the amount of devices or the amount of traffic entering or leaving your network. In terms of devices, it totally depends on the number of users that this firewall is going to support and help protect. Another important security appliance is known as the next generation IPS. IPS is an intrusion prevention system. This is an appliance that is used to detect and block security threats either on a host system or on a network. All traffic flowing through an IPS appliance will be screened for any malicious code or potential threat that may try to enter or leave your network. If a possible threat has been detected, the IPS sensor will simply trigger an alert and block the malicious traffic or the malicious payload in real time. This preventing it from actually entering or leaving your network. Intrusion prevention systems are considered to be proactive in nature, simply because as long as they detect a threat in real time, it is going to block it, and send an alert to the actual administrator. The following diagram shows the placement of an IPS appliance on the network. Notice that the IPS appliance is placed behind the firewall, as in between the firewall and the internal network. Simply because the firewall primary job is to filter malicious traffic. So in case something is missed by the firewall, the IPS can be tuned to pick up, detect, and even block such threats before the traffic is sent to the internal network. As more mobile devices are being created, such as laptops and even smartphones and tablets, the need for wireless connection or wireless connectivity is ever growing and demanding. One such device that will allow our wireless device to interface with a wired network is called an access point. An access point is used to extend a physical local area network onto a wireless network, thus allowing users with laptops and smart devices to connect to the corporate network or even your home physical network. These devices simply emit a radio frequency either on the 2.4 GHz or the 5 GHz wireless spectrum. All modern-day laptops, smartphones, and tablets are capable of operating on these frequencies. To get an idea of what access points look like, let's head over to Cisco website once more. As you can see, there are indoor and outdoor access points. There are additionally wireless controllers for both cloud and on-premise deployments. On a wireless network, devices use carrier-sense multiple access, but this time they use collision avoidance, CSMA-CA. CSMA-CA defines how a network will respond when two or more devices are attempting to communicate simultaneously on a wireless network, which is defined by IEEE 822.11. Before a device sends a message to the access point or to a wireless router, it sends a request to the access point asking if the channel is free to use. If the channel is free, the access point will reply to the client, therefore telling it that the channel is free to send. The client will now be able to transmit its message across the wireless network, and this happens all the time. So as you can see here, we have two devices, A and B. If A wants to send some sort of message on the wireless network, A will first ask the access point, hey, is the channel free to send? The access point will then reply and tell device A whether the channel is free or not. If the channel is free, then A will proceed to send. But if two or more devices send at the same time without asking or verifying the availability of the channel, there may be a network collision. Another device that is new and upcoming is called Cisco DNA Center. Cisco DNA Center is an application used to manage, automate, gather analytics, and integrate security into a Cisco network environment across multiple devices and platforms. Cisco DNA provides a single pane of glass to efficiently manage your network better, automate tasks such as configurations across multiple devices on a large enterprise network. It is also able to provide security insight on threats using Cisco StealthWatch and Cisco Identity Services Engine ICE. In the last domain, we'll explore how Cisco DNA Center helps make network engineers into network developers. Another component is called a wireless LAN controller. On a corporate network, there may be a lot of access points located at various locations, either on the same compound, as the IT department, or even at a branch location that is very, very far away. Imagine having to make a change on one access point at the head office, but also make the same change across all access points throughout the entire organization. This can be a very tedious and challenging task, especially very time-consuming if this task has to be manually done. A wireless LAN controller, or WLC, can be used to centrally manage and monitor all access points within the entire corporate network using a single management interface. So we can think about you as the network administrator. You can log in to the wireless LAN controller and make your changes. The wireless LAN controller will then push those changes to all the access points across the network. So you don't have to log into each of these and make any changes. You do all the adjustments and configurations on the WLC, and the WLC will take care of everything for you. And lastly, we cannot forget about end devices and servers. End devices or endpoints are devices that are used by a person or an employee to perform various tasks for their job duties. These devices can be laptops, PCs, smartphones, or even tablets. There's also servers. A server is a device which runs a server-type operating system, such as, let's say, Ubuntu server, or even Microsoft Windows Server, which are used to provide resources for the clients or the users on the network. In this video, we explored various network devices. We covered the understanding of how network traffic is transmitted between routers, switches, and even hubs. And we look at a little introduction about controllers, which is Cisco DNA Center and even wireless LAN controllers. In the next video, we'll take a deeper dive on understanding the OSI model and the TCP/IP protocol suite. I hope this video has been informative for you, and I hope to see you guys in the next one.